You as well. Okay. So, welcome everyone to Deep Learning Adventures, and thank you for joining us on this Wednesday evening, or maybe not evening, depending on where you're joining us from. I'm going to do a few announcements here at the beginning, and then we'll get started on the main event for tonight, which is a couple of uh, segments on reinforcement learning. So, first of all, we'll move to, let's see, it's probably this one. So this is tonight we'll be doing the Kaggle Competitions, Halite by 2 Sigma, and Hungry Geese, and we'll have two talks. They'll be given by Dmitri Livonian. Sorry, I screwed up your name there. Dmitri Livonian and Alexandra Amadon is going to be giving the other talk, and Dmitri will be talking a little bit about the Halite by 2 Sigma, and Alexandra will be doing the Hungry Geese, a little overview of a different competition that is currently active on Kaggle. And this is our meetup page for this event. This is how you probably found us. You'll see on here there are links to some other useful resources that we hope you are able to find use for as well. We are on YouTube. This link right here will take you to our Kaggle course playlist, which are on George's channel. I'm joined here tonight by George Zoto and David Patton. The three of us have been running this meetup since its inception. So it's a great privilege to be with you all. This is the place where you'll find the Deep Learning Adventures Kaggle courses, which we have recently gone through. We have finished most of the courses now. We did recently discover that a new course has been added, so I'll describe that briefly, as that will be an upcoming event as well. Let's see. We also have a Slack channel, so we'll be putting the invite link, but this is our Slack channel. Anybody who would like to join us, please join via the invite link. It looks like somebody just did because I just got an automated message from Slackbot there. Wonderful. Let's see. We have a couple of upcoming events that I want to be sure to talk about, and that will be here. Next week, next Wednesday, we have the Pedals to the Metal Adventure number 2. And that'll be a second deep learning day trip into the Washington, D.C. Capitol bike share data. And that session will be split. I will lead part of the session, and Kathleen Perez Lopez, right on cue, has entered the meetup, and she will be speaking about a different analysis related to the same data set. That'll be next week. If you recall correctly, if anyone was with us 2 months ago, we did the first iteration of Pedals to the Metal, a deep learning day trip, in which I presented the data set and the pipeline for ingesting the data and a variety of data analysis, but we haven't yet gotten into predictive modeling. So I want to commence that this coming week. If anybody would like a review, you can check it out on our YouTube site. I think it's this link right here, Pedals to the Metal Deep Learning Day Trip. So that is next week, and I think we do not have another event posted, but if it is the 21st going to be our Kaggle AI ethics?
Yep.
I think that's the date. Yeah. Okay. Introduction to AI ethics. This is a brand new course from Alexis Cook at Kaggle and Var Shankar. And we'll be going through these 5 modules on the 21st. Intro to AI ethics. We'll be covering some very important topics related to deep learning, artificial intelligence and how one can be aware of potential sources of bias and other unintended effects that could result as a side effect of applying artificial intelligence methodologies. So, one other important announcement is that this will be a look at our very beginnings. Our very first event with Deep Learning Adventures was Friday, April 3rd, 2020, which means that we are celebrating a birthday this week. This is our first event after the 1 year anniversary. So, congratulations to George for starting us, for getting the ball rolling. It's been a great privilege to work with you and David and all of the friends, both old friends and the new friends that we've had the privilege to meet over the course of this journey full of adventures. So I look forward to many more. And that, before we move on to the events of this evening, are there any other announcements or other items that anyone needs to share or wants to share?
Not from my end. Welcome, everyone. Good to see you.
Wonderful. Welcome again, and we will kick it off with the Halite by 2 Sigma. I believe Dmitri is going first.
Yep.
So I will stop sharing.
Okay, let me share my screen. Oh, it says host disabled participant screen sharing.
My mistake. Can you try again?
Okay, yep. So let me see where. Oops, sorry guys. Okay, yeah. Can you see my screen?
Yes.
Okay. Yeah, so when we discussed how we would approach Halite, so the idea was to have one in-depth session, which you guys had 2 weeks ago, right? Actually building the bots and making sense of the competition. That was a great talk, by the way. I'm sorry I couldn't join. But then we also talked about, if we could have a sort of a debrief session, just going through some of the top submissions and discussing, the strategies, and maybe, looking back to what we did and thinking about, what could have been used. So this is the debrief part, and what I did is I actually shared a brief table with top submissions like an hour ago on Slack, and let me actually do this. This black thing, the black plaque with Zoom is actually hiding the, let me close it. Okay. So I put together this brief table describing the, these are 7 submissions among the top 10 teams. So these are the teams that put up the write-up on the Kaggle page, and also they made their GitHubs public. So I went through the GitHubs and through the write-ups. Before going into maybe a few individual submissions, just several high-level observations here. First of all, I was surprised to see, the dominance of rule-based bots. And in the discussions, there was someone mentioning that, in the previous 3 Halite competitions, because this is Halite 4, right? So there have been previous 3. So all of the top 10 submissions were rule-based. So this is the first year, at least some machine learning made it to the top. Before, everybody was rule-based. So that was surprising, even more so that as you mentioned last time, the number one, the winner, is an ex DeepMind guy. So he was in the midst of deep reinforcement learning and Atari games and all of that, but even he decided to go with the rule-based bot and heuristics as opposed to DQNs. So that was number one, which was very surprising. Number two, I think, if you look at some of the other competitions, typically what would you see is like a fair, concentration of approaches and methods and, code bases, etc. So there typically aren't many different ways to, get a good score on a typical problem, right? In computer vision or NLP or anything of that sort. Here, it was, anything but that. So it was absolutely diverse and sometimes, very different strategies played against each other for, dozens of rounds and, basically ended up with the same score. Number one, number two, and number three, approach the competition from different angles. Some of them put more stress on the Halite collection and guarding the plantations and all of that. Some others do hunting, like number one is to hunt for opponents' ships and basically steal their Halite, etc. So all of these competing strategies appear to work well, even in the top 10. So there are different components used by people. So the third observation I would make that even the two machine learning based approaches that actually made it to the top 10 are not actually reinforcement learning per se, right? So this is not a deep reinforcement, Q network. This is not a DQN. This is not like policy gradient method. This is simply basically what they did is they scraped some games historical and some of them scraped like tens of thousands of games from top players, and then basically did a pure machine learning sort of supervised learning type of approach where each input, so the board with the combinations, with the coordinates of the ships and the halides, etc., is mapped to successful actions, and so they learn actions by mapping the state to whatever was the action was taken. This is called imitation learning, and so both approaches, ML approaches in top 10, actually use this technique. So some participants discussed, why the DQN approach didn't work in this case. So there are hypotheses like very long episode, like 400 steps is too long to actually basically propagate the signal and assign credit, which step actually led to the successful outcome. So one other thing was mentioned that maybe 4 players on the board at the same time is not something, it's more difficult to actually generalize compared to more like, single player Atari or, double player Atari stuff. So it was more dynamic and more diverse. Maybe, the space was more sparse as a result of, 4 players and present and, using different strategies. So those are, I think, the reasons, hypothetical. I mean, one of the reasons that the number one guy mentioned was, the compute. Basically, what they did at DeepMind was based on, infinite compute. Basically, they could afford doing whatever they wanted. Here it's more limited, right? So that might be the reason. So if we look at the the rule-based approaches more closely, more carefully, so couple dimensions that people differed was whether you keep the past history as an input in making decisions at this point, or this is a purely stateless sort of Markovian approach, right? So all we have is the board, and we make the decision based on the board. Even here, people employ different strategies. So I find it interesting that the top two submissions were actually both stateful. So they decided, that the history of, how they came and basically what strategy that they started with was influencing the decisions they're making at the current step, as opposed to the others like number 4, 6, and 9. They're stateless. So basically, their bots are looking at the board as it is right now, and disregarding the past history. And actually, some of them mentioned that in their opinion, that was a strength, because it was sort of discounting the past mistakes that could have been made. So basically, every time looking at a clean state. So this stateful, stateless distinction I thought was very interesting. Another distinction is a strategy for each individual ship versus a strategy player-wide, basically, a general strategy, which then gets channeled and filtered down to each individual ship. I think people approach the game differently in that respect. And again, the top two submissions were coordinated, so there was some notion of general strategy that the player was pursuing, as opposed to just looking at just looping through the ships and then deciding for each ship individually. So another theme which was common in discussions was the abundance of corner cases, and like compared to the simple connect 4 that we did some time ago, or maybe compared to this Hungry Geese 2, right? A lot of corner cases and edge cases, and like the strategy that might work in the middle of the game does not work at the end of the game, because you need to bring your Halite back, and you don't care about how many ships you have anymore, etc., etc. So the strategy very much depends on what in which stage the other players are. And so I'm amazed actually any rule-based approach works, and it's probably explains why the winning solutions are really like massive Python files. Like the winning approach was 11,000 lines of code, and 5,000 lines of code is not a small bot either. So these are really people thought through all the different patterns and combinations that that could happen. Like in contrast to that, which was I thought was very interesting, that the number 5, which was machine learning, computation learning, only used 250 lines of code. And if you go to the GitHub, you just 100 lines or so PyTorch training, and then about 100 lines of inference, basically. Very compact and scalable solution. So another thing I thought very interesting, that the imitation learning was possible at all, and I think this is kudos to Sigma and the Kaggle team, right? That they made the SDK available, so you could actually download, because I didn't think it was possible, and I'm not sure if it's possible, by the way, in the Hungry Geese. So it would be interesting to see. because that seems like an sort of an easy shortcut, right? The rule-based bots are doing all the hard work and thinking about different patterns and strategies, and you can download it and filter it according to some criteria, maybe the winning score, etc., and then just basically try to imitate what they do. So I think, in terms of the high-level overview, I think that was pretty much what caught my attention. Let me know, guys, George, Robert, if we want to go into individual submissions.
Oh, this is great, Dmitri, and really appreciate you putting this this table together. It really shows you what approaches were there and how popular they are. And I like the line of code as well, and the links you shared. I was looking at the first the winner solution and his approach, and he also mentioned that he also borrowed a lot of ideas from other competitors.
Yeah,
it was very interesting.
Yeah.
And it was interesting because in the beginning, he, like you mentioned, he tried a DeepMind approach, and then he said basically all my ships were just sitting still, and then it was taking a lot of time to train. So he tried other rule-based approaches, and midway to the competition, he was like on top, and then somebody came up with a hunting strategy and completely destroyed his agents. So then he had to adapt to that and make a hunting strategy as well. So I found that interesting.
Yeah. It's if he has a very detailed write-up, actually, this the top guy, and there is by the way one other detailed write-up, this number 8, which if you're interested, you could go, and I mean it's really people put a lot of effort. Like this is a few months of team effort to actually come up with these winning solutions. So people describe in detail like how they guard their shipyards, how they hunt opponents, what they do to distract opponents, right? So to basically to push them away, to keep them away from their shipyards. How they guard plantations, why they don't collect halite right away and let it grow, because it grows right at 2% per step.
Yeah.
So people thought about all of these patterns and like tons more. So it's really amazing, the sheer amount of work people put into this.
One that I find interesting is when you corner an opponent and you need multiple ships, and then you have to basically allow only one escape route, and then you have to somehow compute an intersection path so you can get him or her. That was interesting. Right. Another one, if you are cornered, if you are cornered and then you need to send your ships to rescue one of your ships that is being cornered.
Yeah.
Called the rescue mission. And it says this logic is very involved and is not something you should mention in your resume. I'm like, why? Right. Found that very fun and interesting.
Yeah, some hunters, they actually hunted in packs, right? They deployed like 2-3 ships to an opponent area. Like when they saw like a large elephant over there, like with a lot of halite, they deployed 2-3 ships. If the strategy, if they have like available ships and they hunted together, so it was really sort of, you could study an ecosystem, almost. It's an interesting exercise.
There's a question in the chat about if any of them revealed that they had a military background, like any of the winners.
I haven't seen them.
You didn't see it? Okay.
But DeepMind, I think DeepMind qualifies as a military background. Right?
Or if you play now video games, I think you might have some.
Perhaps played Battleship as children.
So it would be really interesting to see, how, if any of these limitations, like about DQNs, etc., apply to the Hungry Geese. I think because the environment seems to be simpler, even though it's multiplayer, but the board is simpler, and it seems to be more tractable. Would be interesting to maybe to participate. Yeah.
So just to clarify, you mentioned this imitation learning, they required basically thousands, or in this case, hundreds of thousands of episodes or training samples. That was the main challenge,
yeah.
as well as the length of each episode is 400 steps.
Yes, yeah. So I think 100,000 training samples means episodes. Yes, episodes.
Oh, wow.
They downloaded. By the way, they also did augmentation.
Oh, wow.
So many approaches look at the ship, the ship level approaches. They basically normalize the board, right? So everything is ship centered. If they look at this ship, they, the entire, the rest of the board is normalized. They also do, wrapping, like basically, you could imagine that all of their ships are in the center of the board at any given point of time. So, and especially number 8, the ML guys, they augmented their samples. I don't exactly remember what they did, but they came up with maybe like a simple reflection would do, or something along those lines.
Dmitri, do you remember for the imitation learning ones, what kind of labels they put on there? I mean, was it the ends?
Labels were the actions taken at the step. So the features are the 21 by 21 boards with some feature vectors in terms of the halite amount and ship positions, etc. So those are the sort of the states, right? And actions are which were recorded. Actions are the labels. So they mapped features to the labels.
So if I remember correctly, when you play an episode, you have the option to download a JSON file. I don't know if that JSON file has all the steps that every ship took, or did they look at the image and try to reverse engineer and replicate? What was the action taken?
I think they had the actions. I'm not entirely sure, but I think the SDK, because Kaggle people, they discussed specifically how they made the episode scraping possible and available, because so many people ask for that. So I think if they sort of specifically responded to this demand, I think that they would have made it available, because everything else is fully transparent, right? So it's there is zero stochastic element here, right, in the game. So everything about basically all of the ships and halites and etc.
Yeah, about your opponent's location, their shipyard. I don't think you can tell how much halite they have, though.
No, you can. Yeah, I think you can. How much halite do they have, because you decide whether you want to attack the ship based on that, right?
Okay. Cool. Thank you, Dmitri. This was super useful. Sure. Any more questions for Dmitri? Feel free to chat or unmute yourself. Cool. If you don't mind, stop sharing in the meantime. Sure. Okay. For Alexandra. Cool. Appreciate it, Dmitri. That was super useful.
Hello. So let me share my screen. I am going to talk through the Hungry Geese game or experiment. Can you all see my screen just fine?
Yes.
Okay, cool. So Hungry Geese is similar in concept to Halite, but it is a lot simpler. And it's based on the game Snake. So I'm just going to pull it up. Basically, you have this little snake, and it wants to eat these fruits. You move it around. And each time it eats a fruit, it gets longer. Hungry Geese is a little bit more complicated with some changes. So the idea is you have 4 players on a grid, and the grid actually it wraps around, and you have 4 actions. So you can go north, south, east, or west. And an episode can last up to 200 moves. And so your goal is to stay alive, so don't collide with other geese. Your goal is to stay alive, so don't collide with other geese. But then you also have to eat fruit. So every so often, 2 fruit appear on the board, and you eat the food by going over that cell. And actually, after 40 rounds of not eating, your goose loses a segment. When you eat a food unit, your goose gains a segment. And so if your goose loses all its segments, so basically your goose never eats anything, then after 40 steps, it just dies. In terms of collisions, like it's the goose that collides with another goose with their head, that is the one that loses or dies. So that's typically the way like a goose will exit the game. So just some highlights, or to recap basically the way the game works. It's a lot simpler. So again, you have 4 things you could do instead of Halite, where the action space is much more complex. Another nice thing about the way they describe Hungry Geese is they give you a way of like defining what a reward is. So of course you want to be the last goose that's on the board, and you want to last the longest. That would be like winning the game. However, even if you don't win the game, you still need some way of like rating how well your agent is doing. And so they define a couple of ways of doing rewards. So here they say your reward that you tell your agent, typically something that is trying to learn, is your current turn times the goose length. So the longer you last, the greater your reward for just being alive. And then if you reach the end of the episode, and I guess you could have multiple that do, this would be your reward. And so the idea of reward we'll touch on when I start talking about a deep learning reinforcement learning agent, and this will be a lot more applicable there. So I think the next step to do is to show how the game works. So the first notebook, actually, let me give a summary of the 2 notebooks that I'll talk about. So I have 2 submissions to the competition. One is a simple agent. It's just heuristics. And I didn't put a lot of effort into it. It's more of getting a hang of the game, how it works, and some of the basic mechanics. And the second was a deep reinforcement learning, a deep Q network agent. Both of these are low effort in a way based on like other work, but really for me, my goal was to like get stuff working and see the mechanics of like reinforcement learning for this problem. And as you can see, the deep Q network did better than like the simple modified agent that I made. These public scores are scored in the same way as the Halite competition. So agents with similar scores will be pitted against each other and play against each other. And based on how they perform, they'll either gain or lose score. This one I just submitted, so it has fewer games played, but as you can see, when it first started, it got a bunch of positive, numbers to its score.
Is it true what Anya told me? I was so
Sorry?
happy that you left.
It was just a muting thing. I'd love to see an episode play, Alexandra. And how many
sure.
are there at each time?
I'll play the most recent one.
I think you stopped sharing, by the way.
I'm sorry?
I think you stopped sharing.
Oh. I must have clicked a button.
That's okay. It's bringing back my Nokia game, snake game memories.
Okay, so here's the most recent game with the deep Q network. I'm the blue goose right here. And they all run around. Blue goose is doing nothing. You can see that some of the other geeses are eating food and getting longer. My blue goose finally ate one, and now it's longer. Some of the geese are pretty long. And my goose died because it ran into the body of another goose. Actually, I think the other goose ran into my body at the same time. So I'm not really sure who lost there. But that I think is helpful. Maybe a helpful way of seeing how the game works. Maybe another one you could see is like with this one. This is a modified version of the greedy agent. maybe not one where my agent like loses horribly. Here, this one, my agent wins. And so I am the red one here. And this one lasts 82 steps because the others lost. So the greedy agent is really trying to just go towards the food. And I'll describe my modification to the greedy agent. So as you see, they have different lengths. My red one is still like in it and still doing things.
I like that they're so coordinated and not running into each other.
Yeah. So the others died and mine is alive. And my greedy agent is very long. So it kind of looks like the reinforcement learning agent had a very different strategy. So really length isn't really the goal. It's just, I guess, the goal there is survival, which maybe getting longer is not optimal.
Cool.
So let me describe the two agents. So this baseline is just simple heuristic rules. Here I play, this is another, here I'm just playing the default agents. I'm playing the random agents against each other and they just take random moves, and this game lasts 5 moves. I think they all run into each other. So the other one I played was against all the greedy agents together, and it's very similar to the game you saw previously with my heuristic agent. They all go for the food and get really, really long.
Does all the food have the same food units?
Yeah, so you get food and it makes you longer. And if you go 40 moves without food, you lose a segment. If you're a single segment, you lose the game altogether.
Yeah, I thought it was interesting that the food is different foods though, right? There's donuts and pizza and pepper, and I thought maybe one was healthier than another, or would do better for the goose than another.
No, I think they're all the same. They just look pretty for the user.
Okay. High calorie burning goose.
It's interesting how the geese get longer. Anyways, so let me talk about the simple greedy agent. So in like the SDK, if you go like to the GitHub repo for the Kaggle Environment's Hungry Geese portion, they have implemented a greedy agent. And so I took that greedy agent and I made a small like modification. So I noticed like as I was playing these games, like agents would like get stuck. So if there's like 2 moves they could make, and one would make them like, so like say this blue goose their head is right here. They don't, or I guess I don't know, say their head is right here. They could move here and get stuck and they have nowhere to go. Because this goose is right here. They have their body right here. You can't hit your own body. And so they have nowhere to go. They get stuck, they die. And the great, like, if you have like 2 like options that are like equally good, you could make these like silly little mistakes, like getting stuck and then you die and lose the game. So what I did was I basically did a 1-step look ahead to try not to get stuck. So basically, you look ahead and see, hey, if I go here, will I get stuck? If yes, then don't go there. So let me show you the agent. I think the code, like just reading through the code of how this was done was actually really interesting. So this agent is actually somewhat stateful in the sense that it wants to know what the last action was. So one rule that I didn't mention before is like if an agent goes like north, it can't go south the next move because it would just kind of turn on itself on its own body. So there's really actually just 3 actions it could take. It can't just immediately reverse direction. So the statefulness is just knowing, hey, which direction did I go in the last move? So I guess the way the agent is called, it gets the board, it gets like information about where the food is from the observation for the geese are and for the opponents are. And so it has a bunch of rules. So the first rule is don't move it next to any head, because if you move next to a head of another goose, you could die. Also, don't move into any bodies, so don't die. And this is the part that I added, so don't get stuck. And so I looked through the 4 possible actions, and I looked at translated each possible action into where the next position would be. Then I looked at the next 4 possible actions, avoiding like the opposite direction, because as I said, that's not allowed. And then I looked at those 3 actions, and if the subsequent positions, not the next position, but the next position, is not in the adjacent head position, because we know about that, and is not in the bodies, you would say you have at least 1 move. And so if you have more than one, if you have 1 move or fewer after taking this action, then it's a stuck action. So you don't want to take that. Does that make sense? Okay.
Are you assuming that the other geese are just going to stay in place for that, for simplicity?
Yeah, it's not really factoring in what the other geese will do. It performs marginally better than the simple greedy agent. So like on average, it is slightly better.
Is staying in place an option? I thought you had to go left, right, up, and down only.
Staying in place is not an option. You have to return an action.
Okay. So you have to move basically.
Yeah, if your agent stays in place, you lose, I guess.
It looked sometimes like the geese were, so to speak, almost playing chicken with each other. Like if one was more aggressive and going for the food, the other would back off.
Yeah, and so that's part of like, so for the greedy agents playing against each other, that's avoiding moving next to heads, and that's avoiding moving next to opponents. The other thing I didn't mention is, so there's, what the agent is really trying to do is select the action that minimizes the distance to food. So there's this function that says, what is the distance, like the distance from the agent and the nearest food. So basically move towards food, but don't take that move towards food, like don't take that minimal action if it's in one of these like forbidden groups. So don't move next to a head, don't move into a body, don't get stuck, and don't go the opposite direction.
Was there anything with like how the outside border, you know how the snake would go up and leave the screen and enter in the bottom? Was there anything like with distance that took that into account? Because you would think like if it was, say for example, if it was real long, you could exit and like come up the bottom and stay out of the middle and not get as tangled or something. Yeah,
I think the distance function accounts for that. Again, like my modification to this was the segment of code. The rest of it is actually part of the default greedy agent. So part of the thing that really helped is because I was modifying something that already existed, it made it easier to pick up the SDK and not have to like, search through everything to figure it out.
Apologize if we covered this, but if 2 geese run into each other, they both die, or the one that attacked the victim dies only?
I forget. I think they both die.
Because that way, I mean, if one of them survives, then maybe you have like a hunter strategy.
Yeah, I think they might both die. Let's play a game because I forget. It's a good question. I was just thinking about that.
If that were the case, you'd almost want to have a defensive move to coil around yourself to minimize your exposed perimeter.
Yeah.
Right?
These greedy agents are really risk adverse. Oh no, it's okay. So the blue one ran into the green one, right?
Okay, let's see.
And it died. So see how the blue one basically is right here? It got stuck. So it could either turn on its own body, it could turn on the other body, or that body, right? So my agent was trying to avoid doing stuff like that. So the green agent didn't run into the body. So basically this greedy agent died because it had nowhere else to go. the greedy agents are risk adverse, as you saw in the code. They're avoiding things.
So regardless of the length, right? Even if the blue one was longer than the green, it would have still died.
Yeah, because it ran into the body, whereas the green one, I don't know, maybe it has some protective shell and the head is vulnerable. You can make something up.
So if the goose has no length, or if it only takes up one square, it can actually go back on itself?
No.
Go back, meaning what? Yeah, right?
Well, I thought maybe you could take a step south and then immediately go back north if the goose didn't have a tail, right?
No, I think that violates the rules of play.
What is the minimum length of a goose? 1 or 2 cells?
1. Yeah. And so if you go 40 moves without eating food, you're out.
I see. So you can go on a hunger strike for 40, 30 minutes, but eventually you have to eat something.
Okay. And so I did play one game with the greedy agent versus the, actually, I think this one is just against itself. So this is the modified greedy agent. And of course, one of them has to win eventually. And because it's so similar to the greedy agent, I won't play it. I think we already saw some examples of it playing in the competition. Are there any questions about the simple approach that I did?
Very interesting, Alexandra. Thank you for sharing.
Okay, so the next one that I'm going to talk through is I started with somebody else's notebook, and they made a changelog, and they have 122 versions of this. So they put a lot of effort into it, and my goal was to take it, make a small modification, and just get it to run. And so they are training an agent using reinforcement learning, and in particular, they're using a deep Q network and the Stable Baseline 3 package. And so Stable Baseline 3 is built by, I think, OpenAI, and it's a package of reinforcement learning algorithms. One thing that took a little while as I started approaching using like a reinforcement learning approach to the task is what library to use, because I didn't want to code anything from scratch. I thought about using a simple Q network, since this, I'll describe a Q network in a moment. However, the number of states is quite large, and I also couldn't find any libraries to just do something that wasn't deep. So yeah, it took a while. There are a lot of libraries out there for reinforcement learning. Some like are really like have a lot of algorithms implemented, but have like 2 people maintaining them. So they aren't like, they don't have community support. I think Stable Baselines 3 might have quite a bit of support, but like, I guess my point is there's no like standard library to use for RL. There's a lot of different libraries you could choose from. And maybe Stable Baselines 3 won't be the default library in 2 years. It'll be something else that pops up. So I guess that's maybe the first challenge with just even getting started with reinforcement learning is like, what library do you use? Will that library continue to be maintained in the future? Regardless, this one made sense. It's basically the same library that was used for the Kaggle RL course, so it was also familiar, and I knew how to set up the environment for stable baselines. So there's a lot of different pieces to actually using reinforcement learning for this problem. I think maybe the place to start is just talking about like the algorithm, and then we'll go into like how we use it, because like my goal was really, how do I get the algorithm to work? I spent less time thinking about like the setup, like the environment. So the basic like paradigm of reinforcement, let me add this little tutorial as an introduction to RL. I think it's nicely written. But the basic paradigm or like framework of reinforcement learning is you have an agent and it learns to perform actions in some environment to maximize reward. Some agents or some environments give you a reward for every step. Other environments, like you only get a reward if you like succeed in the task. And this ties back to that concept of reward that I talked about at the beginning of the game. So these rules of play, they define like what the reward should be. And these rewards are very important to training your agent. And they're basically expected by most, like, actually, I think all of your typical reinforcement learning algorithms. And there's actually, like, if you get deeper into reinforcement learning, you'll find there's quite a bit of work around this idea of reward engineering. So like what should the rewards be for like certain like actions or results to push your agent to perform better. So another piece of reinforcement learning that's distinct from traditional machine learning is that your agent and environment interact with each other. So your agent does something, it moves south, and then the environment responds. So it's basically a Markov chain. So at each step, you do something, you get a response in a sequence. A key term in reinforcement learning is the idea of a policy, usually pi, and this is basically the way you choose an action to take given some state. And so your state is just, say in this case, just what the game looks like. And so you could take it as like, if it's a stochastic policy, just your probability of taking an action given what you see. And then of course, the goal is to improve your policy or your strategy in order to maximize the sum of, or rather your discounted sum of rewards that you get from each step. Are there any questions about the paradigm? I figured it's helpful to define some of these basic terms before we use them in the next section.
Can you just talk about that pi that's with the state? And can you just, I mean, obviously you don't need to go into too much detail, but can you just maybe repeat what you said or just a little more about that?
Yeah, so in the simple agent, my policy pi was that like simple heuristic, the rules that I encoded, right? So given the state, so like the board for the knowing where the other agents were, knowing where the food was, given all that information, I choose to move north, south, east, or west.
Is it reasonable to think of that pi as representing some kind of probability distribution conditional upon the state your agent creates some probability distribution over the actions?
Yeah, I think that's often done in a lot of reinforcement learning algorithms. It could also be entirely deterministic. It just depends on, I guess, what this policy is. Pi is just a very common like symbol for like the way your agent chooses to make a decision. So it could take a bunch of code and a bunch of rules and heuristics, and that could be your pi, or it could take a deep network as your pi. A is a very common like symbol for actions, and state is a very common symbol for, or sorry, S is a common symbol for state. And state is just the board, really, in this case. And under the hood, it's how the environment sends you this, like how this environment represents the board. And the one thing we'll see in the notebook is that there's actually quite a bit of work to convert what the environment says or gives you into a format that works well for the agent. But the agent doesn't really know that. That's just like, I guess, auxiliary and part of setting up the problem.
Yeah, I had a question regarding that actually. So when you're looking at the state, are you looking only at what is around you, or are you looking at maybe how long your opponents are?
So
what is the current position?
Yeah, so going back to the idea of statefulness, the state, so like if your agent remembers, if it's stateful, it remembers the previous states, right? So like have some sort of memory about what the previous like time step, what the boards look like in previous time steps. If it's stateless, it just looks at the board as is, and like, given what I see right now, I make a decision.
So do you have access to the complete board, first of all? Do you know exactly which cells you or the opponents occupy?
That depends on the environment. So some environments are fully observable, such as Hungry Geese or Halite. Other environments are not fully observable. So like poker would be not fully observable.
So in this case, you can see the exact location of your opponent and their left. Interesting.
Hey, Alexandra, this is Ted. Going back to the previous question, just in terms of the notation for a policy, I just wanted to comment that in Hungry Geese, you sort of have the same actions no matter where you are on the board. I mean, you're not allowed to go backwards, but you sort of have north, south, east, and west. But in some games, under certain situations, you may be able to do something, and under other situations, you're not able to do it. So like in poker, there may be certain situations where you can't call because nobody's actually raised yet or whatever. And so I just wanted to comment. So the reason why you see the vertical bar in that notation is because it's the probability, if it's stochastic, of each particular action A, given that you're in a particular state and that there are certain actions available at that state. If all actions were always available equally everywhere, then you could just more likely use normal function notation and just say pi of A comma S. But in this case, the vertical bar is just to help remind you that not all actions are available for every state.
Yeah, actually, I would say that this does apply to Hungry Geese because you can't like go to the opposite direction. So given your state, and perhaps actually I would say your previous action is part of your state, given that state and given that you moved north last time, you can't move south. And so that south action is not in your available action space given your state.
Yeah.
I believe those vertical bars are also common notation used for conditional probability, right?
It is conditional probability. And that's exactly the right way to interpret it. So the way you read it is the policy will give you action T, or sorry, given a certain state T, it will give you action T, or each action T has a certain probability given state T. So like this policy depends on the state. The state is a given for this policy. Are there any other questions about these concepts?
There's a question in the chat. I don't know if I can do a good job. Okay, no problem. Something about, are there any convenient ways to configure your environment and state for partial observability, like fog of war, like you would say, StarCraft? I'm not sure if I'm familiar with that term.
That's a great question. I don't know. I'm not skilled at reinforcement learning, but I'm sure there are.
Okay.
I mean, I imagine you might want to try interpolating what that hidden state is.
It sounds like that's more a question about the SDK than about a strategy. Right?
No, actually, it's not really a strategy. It's how your agent like interprets the environment. So if it sees, I guess if half the image is like bogged out, then like it has to like infer what might be there, or hedge against whatever risks because it doesn't know what's in there.
So some
that affects
fuzzy knowledge of the state.
Yeah, so I guess it kind of depends on like how you construct your agent.
Yeah, so there's two levels to that question, right? So if you're just asking the question of how do you represent what you know, there's really no difference, right? What you observe, what you know is what you know. But in a partially observable game, what you may want to do is to store your inferences about what you think is happening in places that you can't see. And so that would be additional information that you would want to store. So I don't know if, Ian, I don't know if that answers your question.
So that might be you'd keep some extra variables for counting cards in poker.
Yeah, basically. So I think we should move to the next section. So they talk about this carpool environment. It's a classic reinforcement learning problem. We won't go into that because we already have a problem in mind with Hungry Geese. And so I'm going to be using the deep Q network, but first we'll talk about Q learning. I guess maybe a little context for deep Q networks is it was developed by DeepMind to solve like Atari games. And it works very well for environments with discrete action spaces. So we have a discrete action space. It's a small action space, just 4, well, usually 3 actions you could take. So this algorithm is quite appropriate. So first we'll talk about Q learning itself. And so Q learning is based off of this idea of like a Q function. And this Q function is your policy. And you want to learn this, like, you want to learn what this function is. Your optimal Q function is just a function of S, or I guess your probability of S and A. So really, and what the Q function is it tells you the value of being in a certain state and taking a certain action. And that value is determined by your policy. And so as you learn your policy, you better learn what is the value of being in a state that, I don't know, being in this state and taking a certain action. Now, of course, Hungry Geese is probably not appropriate for traditional Q learning since there are lots and lots of possible states. I don't know how many, but there's a very large number of states. And so you'd have to fully enumerate all of them in order to learn what is the value of being in a state. So in terms of like, how do you compute that value? You would use what's called a Bellman optimality equation. I won't go super deep into this, but it's worth seeing and, you know, maybe looking at later because this is quite common in reinforcement learning. And basically it defines how you evaluate the value of being in a state and taking a certain action. And it's really an expectation. So you're in a state, you take an action, you get a reward R. And then that's not the only value of that being in that state and taking the action. It also matters like what all of your future rewards will be. And so you take you discount what all of your future rewards will be, or rather the maximum of that. This is an expectation. So you do this a bunch of times and you average it. And so doing this a bunch of time and averaging it, that's the learning of the Q function. And so essentially what this boils down to is a table of all states and actions and the values that you have learned based off of the rewards and the future discounted rewards. So basically, if I am here and I move here, my reward will be one thing, and then there will be a bunch of future rewards you could get. But if I'm here and I move here, you'll have less reward, and there will be, you know, other things that could happen in your game.
For a concrete example, although one that is trivial enough that it was soluble by other methods, those of you who joined us in the fall may remember the micro challenges course from the Kaggle series, and there were 2 micro challenges, one on blackjack and one on airline price optimization. And it turned out that both of those problems were solvable by essentially following this Bellman optimality formality, but on problems that were much easier, where you could essentially enumerate all the states. So I just thought that was interesting. That's kind of the super easy case of what we're seeing right here.
Yeah, so I would say like this Bellman optimality solution for Q learning works if you can fully enumerate all of your states, and you can just iterate through all of your states and a bunch of times, take a bunch of different actions and learn like the expected like reward or value of being in each state and taking each action. So you have to do a bunch of iteration. And it basically boils down to learning a table of values, and then your trained policy will, like, say it's in a, as it's playing, if it's in a certain state, it'll look at the available actions and it'll select the action that has the highest Q value. So I don't know, you're in a state and action east gives you the highest, is higher value than west and south. And you choose to go east based off of this table of values that you've learned by iteratively updating that table using this equation. Another advantage of using, say, just simple Q learning is that it like once you've learned it, it's static and is easy to understand, and it's probably a little bit more stable than a deep network. So there might be like industry applications where if you can format or simplify your problem to being able to be fully enumerated and use simple Q learning, it may have some advantages there. Are there any questions about this? Really, my goal is to emphasize the idea of a value of being in a certain state and taking an action in that state. And there's some value, and it's basically your expected reward, like over the long term, from that being in that state in action. Okay.
So is it, I'm sorry, is it static? Is static mean that you're assuming no changes in all the other geese, or how are you anticipating what the other geese are doing?
Yeah, so it's not static. Okay, so the actions of the other geese like aren't really considered. It just looks, it's, I guess I would call this stateless because it's not looking at the movement or motion. It just looks at the board as is. So this is your state. This is all you know. You don't know any trajectories or anything. And then you decide, given what this picture looks like, what is the value of taking each of the three possible actions?
I guess I meant anticipating the actions of the other geese.
It doesn't, I don't know, it wouldn't do that. There's no like anticipation or strategy. It's quite simple. It's just saying, like, in my experience, I've seen that if I'm in this state and I take this action, I go west, I get the most reward. Or I guess for this green one, the green one is doomed. Yeah, it doesn't do any of the strategy or of any sort. It just takes in its experience and the rewards that it's seen in the past, and goes from there. So it's, you could say it's not strategic at all. It's insular. It doesn't really consider other agents. It's not a smart algorithm in that sense.
I think in the reinforcement learning literature, when you're trying to think about what the other people are going to do, often you'll see the word planning, and then once you start building trees of like different, possibilities, and you're doing planning on it, then sometimes you'll also see them refer to it as search, because they're now searching for high values, amongst this very big tree of different possible actions.
Mm-hmm. So the next thing I wanted to touch on was deep Q learning. So as I've alluded to before, there's a large number of states in Hungry Geese. And what deep Q learning does is it takes the idea of learning this equation, or like learning what the value is of a state and action combination. It basically trains a deep neural network to learn this mapping of like a state in action to an expected reward given its experience and training. And this helps allow you to extend Q learning to problems where you can't fully enumerate your states or enumerate your actions. And so basically the deep network is a function approximator. And they, call it, this is our notation for it, this theta is just the weights of your neural network. And then you have some loss for it. And I'm not going to go super deep into this. I think, I'm still studying and understanding deep Q networks, but I think maybe a key point of deep Q networks is this idea of experience replay. So you don't take one step and then update your network immediately. Instead, what you do is you it also makes the network fairly unstable. So in order to make the network more stable at each step of data collection, the state, action, reward, next state, all of that information is added to like a buffer, so a replay buffer. And then once the buffer is full, you then update the network compute gradient using that mini batch. So this buffer becomes your mini batch, and then you update your network with that mini batch once each buffer is full. And so they point out there's two advantages. So it makes your data more efficient. So you reuse each like transition and mini updates, and it makes the network more stable. And so this replay buffer, the size of it is actually one of the parameters that is tunable in the network. Are there any questions? Okay, let's jump to the code and take a look. Again, as I said before, I didn't write this code. I modified some of it, and I'll tell you what I modified to get it going. Credit goes to the author of the original notebook, who is, let me pull him up. So credits go to the author of this notebook, DQ and Goose with stable baseline 3. I'm trying to find the name of the author. In any case, I think
in the URL,
yes,
or
Victor
his
de la
profile,
Fuente.
to the left of the title.
Here we go. Yeah, Victor de la Fuente did all of the hard work here. I just ran it with a different network, but I think that's fine. The goal here for me was really, can I get a deep queue network to run? And I'll show you why I found the task somewhat daunting, because there's a lot of work to be done to prepare everything. So this first cell is just a simple heuristic agent, so we're going to skip it. And here we'll get into the interesting thing. So the first thing that you need to do in order to train an agent is you need to actually create your own custom environment in the OpenAI gym format. And so OpenAI, like gym, is a common Python package for defining environments for reinforcement learning. And it's a standardized interface, and the Kaggle Hungry Geese environment doesn't use it. You have to build that yourself. So that's daunting task number one. And then there's a lot of things you need to do to like pre-process like what you get from the environment into an actual grid. So say you have a matrix, you then need to encode each thing into the matrix. So food, if it's if it's empty, it has another value. You need to represent tails, bodies, heads, your own head somehow. And so all of these things are things that their code does. So their code takes like this board and encodes it into a numeric matrix, and each value has a different meaning, and your network can learn like what to do based off of like the meanings of these values. And the author, Victor de la Fuente, put in a lot of effort to like refining and tuning what these values should be in order to like guide the agent to do the right thing. Let's see, I guess, yeah, let's take a quick look into it. So one of the things they do is they actually have a class that is all that it does is it processes the observation. So it gets an observation from the environment. It's a dictionary telling you about like where things are on the board. There's a bunch of utility functions. These actually come from the SDK, but put it into this class. And then they have this function pre-process environment. And basically what this does is it finds all the things that are on the board and then puts them on the board in a grid matrix format. So they also have a function about common sense rewards. So I think this is where they give the agent rewards for doing certain actions, and gives it positive rewards for like dying. Negative rewards for dying, positive rewards for eating stuff, for doing safe things. Let's see. The other thing that's important is to define the environment in this gym.environment class format. And there's a couple like required functions for it. They define it in stable baselines package. And I don't know if this format is required by all reinforcement learning libraries. Maybe some don't, but I think this is probably pretty common across RL libraries. Stable baselines does require you to turn your Hungry Geese environment into this format. So basically it sets up the environment, sets up some default parameters. It has to have a step function. So what happens when you take one step? That's a lot of code. You have to be able to reset it, and then they have a render function. And the thing I want to highlight here is this is a lot of code. So they have the observation preprocessor, and then they have like the environment itself. This is a lot of code just to even get started with training an agent. And of course, it's all important, but I view it as like a big barrier to just getting started. And even just like the step function that they implemented was quite complex. And I think this is where they're like talking about like rewards and ranking, and you want your agent to like try and be a better rank.
Is this code called at every step, Alexandra, or is this called?
Yeah, so this is the environment that the DeepQ network uses to play games. So the DeepQ network could spawn off like, I don't know, 5 different environments and run them in parallel, and then take the information it gets from each game to like update the network itself.
So it's very resource intensive then, basically, right? I mean, you're training multiple games in parallel. Is that what you're doing?
I think that's what it is doing. Actually, I should probably turn off the GPU accelerator. You only have so many hours of GPU per week here. I tried training it without the GPU, and it was really, really slow. It was less slow with the GPU, but still, it took a while. So here they set up the environment. There's a way to check it. And then they use the environment to train the DeepQ network. This is the class definition from stable baselines for the DeepQ network. And you can implement a custom policy as well. So there's some things you have to set up for the DeepQ network. You need to like set up this monitor, which allows you to like track performance over time. Here we define a policy and the like arguments. And so here I'm modifying the network architecture, and this is just a multi-layer perceptron network, and I modified it from the original notebook, and I just have the size of all of the hidden nodes. Just this, I wanted to like run it, see what happens, and I wanted to run something slightly different from what they did. They implement, under the hood, the network is using PyTorch. So here they also implement a custom like declining learning rates. So as you keep training, you learn, like your learning rate declines. So then you have all of these parameters that are related to the network. And I tweaked these as well, just to see what happens. So you have your learning rate function, of course. And I don't know what all of these mean. One thing to highlight is the buffer size. So this is like the experience replay buffer. So how many like experiences do you need in your mini batch in order to update your network? And then you have your DQN, which is just a class from stable baseline. You tell it, hey, I just want to use a MLP policy. You tell it your environment, and this is just an instantiation of your environment class. Your policy keyword arguments is just your network architecture, and then the other params just tell you about these are the parameters that go into the DQN above here. So these are just those params. And then honestly, I think this setup was kind of the easy part. You could tweak these fairly easily if you wanted. And I also tweaked some of the alphas just to get things to learn faster. I printed out the policy, what the network looks like. And then I reduced the number of times it trained. So they trained it twice as long as this. And my notebook turned off. My Kaggle notebook turned off. So I just halved it, and it actually finished training before the notebook turned off. So yeah, it can take a long time to train. And so I guess I don't know like what the right number of times to train the network is. Like, is this enough? Is it too many? If I stopped at halfway through this, would it still be okay? I haven't spent the time like iterating on some of these parameters. Like, I guess like for me, like my curiosity lies in like, how do I, so given the setup, which is hard, how do I like train it? How do I like tune it? And so I actually asked in the comments about, so there's a lot of things you can tune. So you can tune things about the network. There are all those parameters that you saw. And so I asked like, so as you iterate, like where is the, like, how do you approach hyperparameter tuning? Because there's so many, there's the network stuff, there's the number of train steps, there's also like the reward function, like the numbers you put into the grid that you give to the agent. And he said that he tried training various architectures from like this is the number of training steps he used. And he submitted a couple of copies just to see how they perform. And so far, he's found that reward engineering has the most impact on improving his agent, and that's more important than tuning the other hyperparameters. So it kind of sounds like if your network hyperparameters are okay, then you get more reward by tuning your reward features than you do by tuning like the network itself. So it sounds like the key is to like get an okay network. I guess of course you need okay rewards, and then you focus on engineering the rewards. So shaping the rewards so that your network like is like tries to learn like the most optimal thing, which is winning.
Can you remind us in your code where you define that reward?
Yeah.
Part?
Yeah, the reward is defined back in the environment, which is really complicated. So observation preprocessor. So I think they've spent a bit of time like tuning these things. So this is just how you define the board. So the board is, I think, what is empty? It's some value if there's nothing there. I guess it's 0.4 if there's nothing there. It's -1 if it's ahead, and so on. So it's basically, it turns it into a matrix of numbers. So there's some value in that, and that's how like the network views like the state of play. The reward itself, which is what you're actually asking about, is in the environment. So we are in this Hungry Geese env class, and I believe it's in the step function. It should be. You'll notice they have a lot of debugging functions. So we're in the step function. So like there's this trainer object, which you take a step and it returns observation reward and an indication if it's done. And they track what the environment's reward is, and then I think they tweak it. So they do some stuff and look at stuff, and they, you know, if your length now is greater than it was in the previous state, then you improve the reward, otherwise you decrease the reward, stuff like that. And so this is like their reward engineering. So if it's done, they actually looks like they modified the reward based on your rank. So if the game ended, like you give a modified reward. So if you were the 4th rank, you get -2 reward. If you're 3rd rank, it's 0. If you won overall, you get 100 reward. And then I guess if the game, yeah. So this is where they do all of it. It looks like they found that like modifying, like if the reward is less than 1, you should move it up. I don't know. They did a lot of work into just engineering these rewards. And so that's what they said they found the most benefit in most improvement. Yeah.
So from my understanding, just to clarify, so you have a board, you have a game, you have a state, you read that, you pass it to the network. The network gives you what? Gives you a reward, or gives you what the next step should be?
The network doesn't give you a reward. The network basically looks at the board as you've like presented it, and it gives you an action. And then this modified, this custom environment gives you a modified reward value for that. So at the very end, it does return stuff. It returns like the observation. So like what the board looks like. It returns the reward. It returns whether or not the game is over, and it returns, I guess there's miscellaneous info that could be returned as well.
So the whole point of the network is to choose the best next action.
Not next action, to maximize like the total long-term rewards. So that's like going back to the queue function. We want to maximize like not just like the current reward R, but like the reward you would expect to see in the future after taking that action with some discount. So it's the next reward you get for that action plus like some discounted future reward. So it's not like maximizing the next step, but like the full game.
Okay, that's useful. Thank you.
Did you notice any iterations where games where a strategy, perhaps a very conservative strategy of just eating enough to survive, so to speak, was effective?
I'm sorry, you're breaking up. Can you say that again or type it in the chat?
Sure, I'll put it in the chat.
Alexandra, that was really fascinating. Thank you.
I think the last thing I have to show, aside from the hyperparameters, which I suppose you can dig into, I haven't dug into as much as I want to. I just, again, my goal is to get this to run and to see how it did. And then next steps are to like work on tuning it and better understanding like the details. So the next thing to look at are like the results. And so you can plot over the number of over time, and this is from like the stable baselines monitor, what is your episode reward, and how long do your episodes last? And so as you run more iterations, like at the very beginning you can see a small improvement, but I don't know, I didn't find this plot to be very useful. I couldn't really tell, like, I don't know, did it like stop learning after some point and it like was just pretty good? This all looks kind of like random noise. I can't really tell if the mean has increased or not.
And each data point is a step in a game?
Say that again?
Each data point is the reward you get from a state, a step in the game?
I think each point is the total reward from a game. So each point is one game, and T represents like, I've trained for 1,000 games. This is how well I've done. This would be after 3,000 games. This is how this is done.
It does look like there's an upslope at the very beginning over the first 30 games or so, 50 games maybe.
Yeah. Yeah, so I guess it's hard for me to tell, like, has it really learned, or is it mostly just like becoming more stable?
So just
Catherine's question is in the chat now.
Okay.
Did you notice any games where a very conservative strategy of eating just enough to survive was effective?
I don't know, because I haven't played a whole lot of games. I think that's what the agent was doing, the deep learning agent. So if we go back to the submission, we can kind of see that. So if we go back to the episodes, and then we play this. Oh, hey, I'm playing against Victor De La Fuente, and he beat me. That's good, because you don't want to, take away from all this hard work. So I'm the blue person. And so you see, I haven't eaten anything yet.
Interesting.
I hope I eat some. Okay, I have eaten something. So I think that's kind of what my agent is doing, is just enough to survive. Although I don't know why my agent made the really dumb choice of like going right there.
There's some uncertainty though about being able to get food in the future, right? You don't want to play that too close.
Yeah. And yeah, so like you lose a segment after 40 moves, and so my guy ate something after 29 moves. And so it had a buffer of like 10. And it looks like, oh, interesting. So both my agent and Victor De La Fuente's agent made the same dumb choice. So like mine died because I ran into his, and it looks like he ran into me. It looks like. It also looks like they took very different strategies. Like his is very long and mine is very short. And maybe like it's something to do with like, I mean, my network was much smaller and I trained it for a different number of episodes. So perhaps it learned something totally different from his. But they still made the same mistake.
That's cool.
Yeah. And then I think the last section is just about saving the model. And I haven't dug into this code very deeply. I just want to emphasize that. So they put in the observation preprocessor into here. They have like a custom class for the network, a function that like runs the network. So again, a lot more code to do that. They put it into a file, run it to make sure it works, and then they play some episodes. And so the network one is the first one, and so you can see how it does. I think this is like the reward or score. But yeah.
So each row is what, a game?
Yeah, each row is a game. Each column is a different agent. The first column is my network. And so you can see oftentimes it did pretty well. One time it did terribly. Mm-hmm. It seems slightly better than greedy, but it doesn't seem terribly better than greedy. But it has promise. It's able to learn strategies and not just do the same thing. Yeah. So I think improvements here would be around like the reward engineering. And I'm still curious about like some of the network engineering as well. So yeah, maybe there's some bugs in the code. There's a lot of code. And I think that seemed to be a pretty big barrier to getting started. It's just the amount of like stuff you have to write around the problem, even though that you have the environment given to you. Just like formatting like the observation from the environment in the right way is time consuming. Yeah, there's a lot of code around the problem that isn't necessarily like reinforcement learning, but it's necessary. So maybe that's the biggest challenge, is the problem setup. Maybe you could equate that to like data engineering or feature engineering and classical ML.
Alexandra, can I ask a clarification question regarding your visualization of a few cells above?
Yeah.
So was the x-axis t, was that, you mentioned games, but is it games, or is it how long a game took to complete? Is it like how many episodes or how many steps?
Episode length would be how many steps it took to complete.
Oh, I see.
If the episode is really short, then the agent didn't do so well. it's long, the agent did really well. So like a longer episode length is what you want. So actually, I think you can see some improvement. Like you get more concentration of like higher episode lengths as you go along.
And is 200 like a maximum episode length, or just happens?
Yes, it's max.
And the x-axis is what again? How many games you're playing?
Yeah, so I think this is like games like so agent will play some games and learn from them. This is like the sequence of games that it's played and learned from. So after 3,500 games, these are the episode lengths of those games that were played.
But this doesn't show you the average reward of each game, does it? No, right?
No, it's specific rewards, not average. There's no aggregation.
Oh, okay.
Yeah.
If you wanted to see how your reward iterates or progresses,
This is it.
This is it.
Yeah, I guess like
Reward.
I took these plots as is. I would want to like maybe draw some like trend lines here and like know what the slope is of like the average and what the standard deviations are.
Okay. I didn't realize the y-axis was different for two of them. Okay, one is reward, one is length.
Yeah. Yeah. I guess you could interpret y as like training time.
Mm-hmm. How long did it take to train this notebook?
Yeah, so under 40 minutes. The notebook turns off after 40. So this got me under 40 minutes. If you double that, it's more than 40 minutes and the notebook dies. So that was one of the challenges, is like train it as long as you can, but like not so long that the notebook dies, because I'm not gonna like sit here keeping the notebook alive while it's training for who knows how long.
And when you're training it, who are the other agents? Are they random or greedy, or did you?
Yes. Yeah, so I trained it against greedy agents. So perhaps like, actually that might be an interesting experiment, is to try training it against, say, this network agent, in addition to greedy agents.
Mm-hmm.
And maybe that's what some people do in their own notebooks, but I don't know.
Yeah.
Yeah, presumably the strategy that would beat a greedy agent is not the same as one that would generally do well against all different sorts of agents.
Yeah, yeah.
Are there any other questions from our community before we wrap up?
Just a quick comment. So Alexandra, that that reward graph that you were showing, I don't know, maybe like a running average or something, you might be able to see if there's an upward trend or not. Take out some of the noise.
Yeah, that's a good point. I think that's what I was thinking in my head, but didn't say it. Actually, I probably would have plotted like the bad average plot, but then realized I needed like a rolling average.
Well, thank you so much to Dmitri and to Alexandra for sharing this really interesting work. We get to see a little bit about the Halite other agents, the winners from that competition, and Alexandra's approaches to the Hungry Geese problem. Thanks for joining us. We look forward to seeing you at future events. Remember, we have the Pedals to the Metal next week and the Kaggle AI Ethics course 2 weeks from today. So thanks for joining. We will shut the recording off here soon. I think we'll do that now, and we'll leave the floor open for any additional comments that people want to, or socializing that people want to do after.